All right, next up, I am happy to introduce Ryan Weald from Sharethrough on productionalizing Spark streaming.
Cool. Yeah, so as you said, I'm basically going to talk about Sharethrough's experience productionalizing Spark streaming. And in particular, what we're going to cover is just to lay down a foundation. I'm going to talk about what we do at Sharethrough, why we needed Spark, and why we ultimately chose Spark for our streaming needs. Then I'm going to talk a little bit about the fault tolerance issues we've seen and had to overcome when you're trying to run long-lived Spark streaming jobs. Then I'm going to move on to kind of the meat of the talk, or kind of the main focus area, which is common patterns and functional abstractions. Right? So I think there's a lot about productionalizing a system that's more than just ops. Right? There's a whole world of tackling software engineering challenges that you have to overcome if you want to be able to run something in production and have large engineering teams work with it. And then I'm kind of just going to reiterate some testing points, because if you're going to productionalize anything, you need to have tests, because if you're not really testing your software, it's going to be very hard to scale it as you grow the company. And as I said, there's really going to be a special focus on common patterns and their solutions, right? I'm not going to talk a ton about the ops issues we had when we were productionalizing Spark streaming. I think that's pretty covered in other talks on other tracks. I'm really going to talk about the software engineering challenges, because I think that's going to be the thing you have to overcome first if you really want to take Spark streaming out of the proof of concept and into the production solution that you can use at your company. So yeah, just to start us off, just a little bit what is Sharethrough? Basically, we're a new age advertising company, so we like to call it advertising for the modern internet. The idea being we want to have ads that match the form and function of a publisher's website. So effectively, we want to kind of get rid of annoying pop-up ads and replace them with nice in-feed units that match the content of the publisher's site as well as the look and feel. Right, why that's relevant to Spark is basically, like most ad networks, we have the problems that naturally come about. Right, we need to do a lot of prediction for clicks, visibility, we need to do contextual targeting, and all of that stuff has to happen in real time, because people are constantly hitting publishers' pages, and all the time you need to be able to serve new content to the user that's relevant, and also you need to be able to understand what's happening on the page so that you don't accidentally overspend. So, why Spark streaming? Right, we evaluated a lot of different technologies when it came to picking our streaming solution. Ultimately, we settled on Spark streaming, and one of the big reasons is we like the theoretical foundation of the mini batch model. Right, so Spark streaming is based on the notion of mini batches rather than a lot of other systems which kind of treat it as a continuous stream. There are a couple of advantages to the mini batch idea. The biggest ones being around aggregation. It also made monitoring a little bit easier. It was also a Scala code base with a functional API. We're pretty much an all Scala shop on the back end, so we wanted something that was easy to express in our primary language. Obviously, it's a young project, so there are plenty of opportunities to contribute, which was definitely a plus. Right? The fact that it's not quite as mature means that if you need to go in there and be able to change things, as we saw earlier, the code base is still not huge, so you have the opportunity to be able to do that. And it also gave us kind of a two birds with one stone type thing, because we can also use the batch model for iterative ML algorithms that are a little bit harder to express on Hadoop, and also harder to express if you have a pure streaming, like Storm. So now that we kind of talked about why you'd want to pick Spark streaming, it's great, okay, now I need you to productionalize it, right? All the guides go through how to do count words in real time, maybe help you count tweets, but you really need to productionalize it. And the first thing that we ran into when we started trying to productionalize our systems was the idea of fault tolerance, right? Obviously, if you're going to run streaming jobs, you need them to run all the time. So if your streaming process is crashing every 2 hours, that's not great. And really, when we dug into all of our fault tolerance issues, two big things came up, and that was really that you need a receiver fault tolerance, and you need monitoring of your job progress. Right? Obviously, if your receivers are constantly going down, you're not going to be able to have your stream run long term, because its source of input data is going to constantly crash. And then obviously, if you're going to be running it in production, you want to know it continues to work, you need to be able to monitor these things. So receiver fault tolerance is actually relatively easy to solve once you know you have to deal with it. Right? The real key is you need to use actors. Right? Using actors rather than your main thread means you can use supervisor pools. Right? This is a concept that's kind of actually native to Spark itself, since it uses akka quite extensively. So you have all of the framework in place that you need. You just need to use these actors, which gives you automatic healing when network issues occur. The second big thing is really self-healing connection pools. right? If you have a connection pool that goes bad as soon as a single connection dies, you're going to run into problems long term, right? Like anytime you have something running for a long period of time, there's always going to be network issues, which means connections in your connection pool are always going to die. And if your connection pool can't naturally heal itself, it will slowly shrink from a connection pool that had 10 valid connections down to a pool that has 5, 4, 3, 2, 1, and then it eventually dies saying, hey, I couldn't connect to anything. All my connections are dead. So if we look at a really simple code example of what this might look like, you can see basically a RabbitMQ stream receiver that uses an actor system. This is obviously just a shell, but the real core here is that you get a lot of this for free. Right? Just by extending actor with receiver, you get a lot of preset programming that automatically gets dropped in for you, and that stuff handles a lot of the automatic actor supervising that you need in order to keep the things running long term. So once you have the basics set up, so you have like fault-tolerant receivers, the next thing you really need to be able to do is you need to be able to track your outputs. Right? And we kind of found there were 3 main ways that we were able to do this, and things we're looking to do now that will really give you the type of reliable reporting that you want if you're going to run it in production. I think the biggest one is this notion of low watermarks that was introduced by Google in their paper on Millwheel. It's the concept that all of your events that go through your stream processing system should have some sort of timestamp tagged with them. Right? Once you have those timestamps, you basically use the last process timestamp to act as like a low watermark, so like the last events you've seen, and that turns out to be a huge win. Right? If you don't have that, what we saw in production is that your JVMs would still be running, so none of your like built-in reporting, like if the JVM crashes, send an alert, none of that would go off because the JVMs would still be running, but nothing will be processing. Right? It could be that you have an exception in your code, so at like the second step in a long pipeline, every single thing crashes, you never get to the aggregation. It could be something like you run out of JVM memory, but the JVM doesn't die. Right? All of these things will cause your events to back up, but not cause the system as a whole to crash. But that means as far as the end user is concerned, it has effectively crashed, right? So using this notion of a low watermark and ability to see when the last event you've processed was is huge. Because if you have that, all of a sudden you can plug that into whatever your reporting interface is or whatever your alerting system is, and it will tell you like, hey, I actually haven't processed a new record. The last record I saw was actually 3 hours ago, which means you probably want to do that. Like you probably need to fix your system. The next thing we looked at was essentially the notion of the simplest thing you can do, which is like a database updated at field, right? Like most major tables and databases that you use, if you use like Rails or Django, will have an updated at. Turns out if you just like push that through all of your systems, you end up with like really good results, right? So just by incrementing a column every time you change a record in MySQL, you get big wins, right? That's what we saw basically just by adjusting a field to updated at. You can pretty easily query your database and say, hey, when was the last time I wrote a record on a click for this creative? And then it's pretty easy to build reporting off that and also alerting. And the final thing is the idea of an expected output size alerting, right? So oftentimes you have some idea of generally how big or small you expect the output of your large streaming jobs to be, right? And this is where the mini batch really comes in handy. Right? Since you have these mini batches, you can have some predictability around how much output you expect from each small batch. And if you use that idea, you can start to build up your own alerting around the output size. Right? So if you expect, hey, I usually get about 1,000 new beacons every 10 seconds, I'm running this mini batch every 10 seconds, and the output I get from my ETL is like 0 or maybe only like 5 bytes, that's probably not a great thing, right? Like I expected to see a beacon come in, a beacon come out. So we got really big wins by having pretty simple expected output size, right? Like most of this stuff is all pretty simple, right? Like low watermarks, when was the last event you processed, updated at, expected file size. Like none of it is really mind-blowing. Most people have been talking about it for a while, but it's just taking these concepts and applying it to Spark streaming as you're getting going will be big wins. So now we've covered some of the basics of fault tolerance. I want to look at the common patterns we saw and how we used functional programming concepts to overcome them. And so when you take a step back from Spark streaming and you just look at streaming and even batch processing as a whole, it pretty much always fits this pattern, right? Like you have some data, you map over it, you take it from one type, you convert it into another type, right? You do all that cleaning. And then really what comes down to is you're going to aggregate it, right? Maybe that's addition, maybe it's some sort of set math, maybe you're using really cool probabilistic data structures. At the end of the day, that's an aggregation. And once you finished aggregating, you're going to store. Right? So if you think of this as a common job pattern, it becomes how do we express this common job pattern in Spark streaming? Because once we have that, expressed, it's pretty easy to write Spark streaming jobs in the same way that all of your engineers already know how to write Hadoop jobs, maybe even Storm jobs. So mapping data, not super interesting. It's something that pretty much everybody already knows how to cover, right? Like all of the examples already do this. I think the biggest win here, if you look at this code snippet, is the idea that you don't really want to do a lot of computation in your anonymous functions, right? Like a lot of user guides and early examples will have you doing regex parsing, all that stuff in line in your anonymous functions. This is not like a massive revelation. You probably want to extract that out into external objects, and that's really what enables your testing, right? Like if you have tons of operations being done in your internal anonymous functions that are tied to Spark streaming, it becomes very hard to test. Because in order to test these things, you have to spin up the entire Spark streaming context, which is going to add time to your test suite. Simply by extracting it out, as you can see here, the query param parser handles all of our raw request parsing. We're able to test that offline, outside of Spark, unit tests that run in milliseconds rather than seconds. And it becomes really pretty simple. So once you've handled mapping, you really get to that next step, which is aggregation. Right? So in all of the basic tutorials, you have this really simple aggregation, right? Like I basically have a sequence, which is clicks, and a number, and I want to get their sum. And that's pretty simple, right? We define a pretty easy function here. Obviously, this is in Scala. That basically just takes our two longs, adds them together. Pretty simple. We say reduce by key on that sum. And just like that, we have one thing aggregated pretty easily. But you run into this problem. What happens when we want to sum multiple things at once? Right? You're not really going to have a job in production, or very rarely will you have a job in production where you only need to aggregate one thing. Right? Usually you want to aggregate a couple things. For us, that means in real time we need to aggregate impressions, visible impressions, clicks across all of our creatives and across all of our placements. So now all of a sudden things start to get a little bit messier. Right? Now we need to sum multiple things at once, and we can't afford to do a split, sum them all independently, and then merge them back together because that's just not efficient computation. So we have the same sum function that we did before, only now it's starting to get a little bit more complex. Right? We have a tuple of longs. And what we have to do is we have to go through each one of these, and we have to add it. Right? This is still not super hard, but you can see the complexity is slowly starting to grow. In addition to that, we've kind of the same thing. We've tied this function into Spark directly. Maybe we could test it externally, but it's going to be a little tricky because it's like a method on our class that has all this other Spark code related to it. None of that stuff is great. And all right, we write this function. It's pretty complex. And now somebody comes along and they say, actually, it wasn't longs, it was actually like ints, and there's 4 of them, not 3 of them. My bad. And so you've written that complex function, and now you have to sum 4 ints instead. You're not super stoked. And it turns out there's a pretty cool functional programming concept that can actually solve all these problems for you, and it's the notion of a monoid. What a monoid is basically a functional programming construct that encapsulates an associative aggregation. For the purposes of this talk, we'll say it encapsulates an associative aggregation. Right? The idea being we have this trait, which is a monoid, and it has basically 2 methods. A 0 method, which returns you essentially an identity operation, right? So adding 0 doesn't do anything. It also has a plus, which is a way of taking any right and left argument that is of the same type and outputting a combined version of that. With the one caveat being this plus needs to be associative. Right? And that means in addition, obviously associativity is pretty easy. So if we take our example from earlier and we convert it to use this new monoid pattern, right, what we can see here is basically the code looks a little bit more complex, but we're starting to get big wins in the sense that this is now a separate object that's no longer tied to Spark. Right? And we've started to express it using this concept of a monoid. And it turns out, once you have this monoid written, the actual Spark code is pretty simple, right? We just say input data, reduce by key, we pass it this monoid, this plus, and the monoid takes care of all of that aggregation for you. So that looks like a lot of code. You're probably thinking, how do I really get a win out of using this monoid? That seems like a lot of overhead. I'll just define it in line. It turns out the real win is that the guys at Twitter have already thought about this, and they've pretty much written most of the monoids you need to use in your jobs for you. Right? So they have a cool project called Algae Bird. This project's basically gone through and it's taken monoids and it's basically made them for most of the common classes you'll use. So if we take this notion of adding 3 longs and we use Algae Bird, it turns out we can do that whole thing in 3 lines. And none of that code is code we have to maintain and we have to test. Right? It's already tested in another code base, it's tested by Twitter, it's used by tons of other companies, and it makes our jobs very, very simple. Right? All we have to do is a little bit of like Scala craziness with the implicits, but fundamentally, we just get a new instance of a monoid for tuples of 3 longs, and we can just pass that to our reduce by key. So you kind of have this idea of a monoid. The real time it becomes a big win is when you start to get more complicated questions, right? Somebody comes to us and they say, hey, how many unique users do I have per publisher, right? It's in production. You're going to have to start answering new questions. People say, you know, I want to know unique users per publisher. The problem for us is that's too big to fit in a naive memory-based hash map, right? That'll be the easy way. I'll just like add users in each pub in a map, count things as a value, not a big deal. It's too big. But there's a way to solve it using a probabilistic data structure, which is essentially hyperlog-log. We don't need to get into it here. It's pretty cool. You can look it up online. But fundamentally, it's still just a type of aggregation. And that's really where this notion of thinking of all of your jobs as aggregations using monoids becomes a huge win, right? Because what you can see here is that there's already a hyperlog-log monoid in Algae Bird, and all we have to do to have this complex aggregation done across large data that's too big to fit in our naive implementation is just have our aggregator be a hyperlog-log monoid, same pattern, aggregator.plus, and just like that, we have a complex aggregation done for us. We can run it in production, we can trust it, we can test it independently of Spark, all of that great stuff with very little work for us. So essentially, monoids equal the idea of reusable aggregation. So once you've aggregated it, you get on to the next step, which is storage. Right now I've counted all the things, I need to go ahead and write them to my database. So how do we store the results? Right now, Spark Streaming gives you some basic methods that will write out to a store for you. Unfortunately, they're mostly around HDFS. We personally don't use HDFS when we're doing production streaming. Most of you guys probably won't in the long term either. Most people end up writing to some sort of other NoSQL database, so you get better query latency. Right? Obviously, you need good query latency if you're real time. HDFS is not great for that. So really, we need a storage API that has some of these requirements, right? It needs to support incremental updates, preferably they're associative, because we need to be able to change the results that are in this database as we get new data, because it's a real-time stream. Ideally, it has pluggable support for multiple big data stores. We have a couple teams across Sharethrough. We're going to want to use different stores for different projects. We'd like to be able to tackle that. And most importantly, we want it to allow for testing. Because if you're only outputting to HDFS, it becomes pretty difficult to test the output of your jobs without having to spin up HDFS clients, which is never nice. So ideally, we want a storage API that looks a little bit something like this. Right? We have this idea of a mergeable store. It has a get, it has a put, and it has a merge. That merge is basically following the same associative property that the monoids earlier followed. And it allows us to just give it data, and it will handle aggregating the results that's already in the database with the new data we give it. So it turns out the reason I'm bringing this up is the easiest way to run this in production is actually just to use another project that Twitter has already tackled, and that's Storehouse. Right? Storehouse contains battle-hardened implementations for most of the common big data key value stores right now. Right? There's like Redis, DynamoDB if you're on Amazon, Hosted, MySQL, Cassandra, all that stuff is already there, and it has this really beautiful property of it all adhering to that same interface. And what that lets us do is it lets us generalize all of the saving of Spark results into the same save function, right? And all of a sudden, every single end step in your jobs looks exactly the same. And that's basically just for each RDD, loop over all of the elements and merge the results from the aggregated result into our store. So we've kind of seen these things in production. Obviously, our code internally has been refactored to use these common practices to make it very easy to run and extend. And really, we want everybody to be able to benefit from that. So I have some ideas for potential API additions that I'd like to work on when I get some time, and would be really interested to see the community's general input on what they think. And that's essentially the idea of an aggregate by key that takes an aggregator that is a monoid, right? And then all of a sudden, we wouldn't even have to do all of that anonymous function, like partially applied functions with the monoids from Algae Bird into our Spark jobs. And at the same time, I'd also love to see a store method, which would allow us to have the end of our jobs, rather than having to be outputs to HDFS or nasty for each loops all the time, just be pass in a store, do all that looping for me internally. And the other thing I'd really love to see is Twitter has another cool project called Bird, which is basically this idea of taking all the things I'm talking about and generalizing it so it doesn't rely on any single platform for computation. I think Spark streaming is actually a perfect fit for that. We're already starting to work with the guys from Twitter to bring the idea of a generic MapReduce using map aggregate store to Hummingbird using Spark streaming. So we're hoping in the future we'll be able to have anonymous, like a Hummingbird platform that would allow you to use Spark streaming underneath the covers. And then the exact same code you can write that runs on Hadoop could literally run 0 code change on Spark streaming for free. So now that we've kind of talked about these functional abstractions we've seen as a whole, I'm kind of just going to close out the talk by just reminding you of a few things that you want to keep in mind when you're doing testing. And that's kind of stuff I've already touched on here. And that's essentially, you want to try and avoid full integration tests at all costs, right? Full integration tests, if you've looked at the code that even Spark internally uses, it basically will do a max sleep time of 10 seconds while it waits for the results of a streaming computation to come in. That's not great for your build time, because every time somebody writes a new test, you're looking at potentially 10 seconds. So the more we can avoid that, the better off you'll be, right? The easiest way to do that is basically try and use code that's refactored away from needing Spark, right? So extract like monoids for all of your aggregations. That way you can test them outside of Spark. Try and refactor all of your map code into separate objects so that it can be used outside of Spark. All that kind of basic software engineering stuff is really the biggest wins when it comes to productionalizing Spark streaming, right? Spark streaming is just like every other big system you use. The better and cleaner your interfaces can be around it, the better it can be. Obviously, the next big win is try and use in-memory stores for testing. That's what we use, right? So once you have this cool concept of storehouse and a generic interface for all of your storage as the last step, what you can do is that rather than having to use DynamoDB when you're testing or even Cassandra when you're testing, you can just inject an in-memory store that has exactly the same interface, will behave exactly the same way as far as your job's concerned, and you can easily test the output of that, right? And that becomes very easy, so you can have high confidence around how your jobs are going to work interacting with a store, and then you just drop in Cassandra when you're ready in production, and you already know that will work. And the last thing, which I think will be great, is once Hummingbird is ready, you could, in theory, use the in-memory platform for Hummingbird to actually execute your tests, right? You could write all of your code so that it works with Hummingbird. Hummingbird allows you to compute not needing Spark streaming in testing mode, and then you'd be able to just drop in Spark streaming in production. And I think that would be probably the biggest win for all of us, because then you wouldn't have to worry about spinning up an in-memory stream processing for Spark streaming. You'd be able to just have the in-JVM, really simple Hummingbird DAG executor, and then just use Spark streaming in production. And that's really all I have for this part. If there's any time, I'm happy to take questions or chat later about the other things we've experienced productionalizing Spark. But yeah, thanks.
Thank you.